So this is week 5 and sir told in this week EM waves in multilayer stack T matrix formulation, and this video is recorded because when I am teaching, so with some technical issue the video was not saved, so I am re-recording this one. So this photonic band gap 1D and this EM waves in 1D photonic crystal, diffraction grating, application of photonic crystal and photonic crystal in one dimensional T matrix. All these topics are covered in week 5. So starting from electromagnetic waves in multi-layer stack, so let's say there are multi-layer stack n1, n2 and n3, and this electric field is coming from this region, so it will reflect back from here, and some partially it refracted in this region, and from this surface this is partially reflected and partially refracted. So but in n3 there is no reflected wave here. So let's say this wave is going to minus x direction, then it will be written as e to the power I kx, and when it is in plus x direction, then it is in e to the power minus I kx. Okay, so the region is defined as x less than 0 for the region n1, and for n2 region there is x less than d and greater than 0, and for n3 region when x is greater than d. So this electromagnetic wave can be written in the first region is a e to the power minus a I kx, which is going reflected wave, it is coming to this side, and this portion due to this region due to this way going to this side, and this factor going to this side. So and the in third region, this one, the I kx and with some constant c and d, but in n3 region there only is wave going to x direction. Okay, so this way is going to this direction, this way going to this direction. So we can define it as the bonding, with the boundary condition we can calculate a b c and d e values. So by the way, reflected wave can be reflection can be calculated with the ratio of b to the a, and the transmission can be calculated with the ratio of e to the a. Okay, so this ratio n1 in n region, b is in this direction, a is in this direction. So this a and v can reflection is can be calculated with respect to incident wave a. Similarly, the transmission e can be calculated with respect to incoming wave, so e ratio to a. Okay, so and there are some d or d inverse which to diagonalize the matrix. So this reflection can be calculated as a n minus 1 n1 minus n2 upon n1 plus n2 to the whole square. This is the reflectance calculated due to the stack region, and this a and v, c and d, this coefficient can be related by some matrix defined as d0, d1 and p. Okay, so this is called the transfer matrix. Okay, so this transfer matrix notation is something like, for the photonic crystal in 1D, if you say there are n1 n2 n1 n2 is the repetition till infinite region, and let's say this is for region a1 and this is a2, so total is gamma. This is gamma 1, this is gamma 2, and this is a periodicity defined by the gamma. So the band gap is dispersion can be written as like this is the dispersion relation between k and omega. So this ray go to this region, let's say this is pi by gamma, the Brillouin zone. Okay, and so the second band goes to like this way. So this region is known as band gap, that is called photonic band gap. Okay, so this is the some dispersion relation for one dimensional photonic crystal. So come to the question number 1. So a typical slab has a refractive index of n is equal to 2.3. The percentage of reflected and transmitted power for visible light incident on a power air slab interface respectively are. So how can we calculate it? We can calculate it from this r, as earlier I showed you the formula, n1 minus n2 upon n1 plus n2. So for this you can calculate it, this r 1.3 by 3 by 3, so it comes around 0.39. okay, so this r can be calculated rd to square, and this comes around, this rd is b by a, which we earlier saw. This a equal to 0, and if we consider a equal to 0, this n is equal to 2.3, n is equal to 1 for this region. So r can be 14.5, then t is equal to 1 minus r, that is 1 minus 14, that is 85%. okay, so this will be your reflectance and this will be your transmittance. So answer 1 is the correct answer for this reason. And similarly, consider a stack of a slab of refractive index n is equal to 1.5 and n is equal to 2. A light of wavelength lambda is incident on angle theta 1 is equal to 45 degree on a stack. So calculate the approximate angle of incident theta 3 at second interface. okay, so this region you can calculate the stack. Here is 1.5 and 2 and it's equal to 1. So here 1 is theta, this is theta 2, and this is theta 3. So by the Snell's law you can calculate it, this n1 sin theta 1 is equal to n2 sin theta 2 for this stack, and this Snell's law is n0 sin theta 1 is equal to n1 sin theta 2. So n1 sin theta 2 is equal to n2 sin theta 3. From this you can calculate this sin theta 3 is equal to 1 by 2 root 2, this sin theta 3. So sin theta 3 is sin inverse 1 by 2 root 2. So theta 3 will be around 20.7 degrees. So for this reason this answer is correct one. okay, so the next question is, consider a slab of thickness d is equal to 500 nanometer and refractive index is 2.3. okay, so a light of wavelength lambda is equal to 500 nanometer and normalized power is 100. So incident on slab. So assume that the incident light undergo to reflection inside the slab. So how can you calculate? So this is rho and tau 1. Let's say d is equal to 500 nanometer. So this 100% power is coming, so it will reflect it to this region and also going to this region, then again it reflected to this region and again transmitted from this region and coming to this region. So and this again. So let's say 1 2 3 4 5 6 points are there. So this gamma is equal to r12 plus r23 e to the power minus 2i kdn, and 1 plus this gamma can be has been derived in the lecture. So this delta is 1 upon 1 minus r. So r can be gamma square, so this t can be 1 minus r. From here r12 is equal to rho 1 is equal to n1 minus n2. So from here this is comes around 0.39, and r, then you can calculate this delta from here, and then gamma, and then t to r. So from this tau 1 is equal to 1 plus rho 1 is equal to 1.39, and tau 1 can be 1 minus rho 1, this is 0.606. So rho 1 dash is equal to minus rho 1. So from this node 1 and 2 node 4 you can write no row 1 dash row 2 tau 1 and tau 2. So multiplying all these numbers you will get this around 0.13. So percentage of transmission is equal to 13% from here. So the answer C will be correct, 1. Okay, so similarly the question number 5, let's consider two cases where light interacts with metallic nanosphere and dielectric nanosphere. Which one is true in the terms of surface charge density? So sigma of surface of metallic will be surface of sigma surface of dielectric. This is wrong because surface is always greater than to the dielectric. Okay, so for this reason this correct answer 3 is correct. Okay, so the next question is stack of layer H is high refractive index, L is low refractive index, like that. So such that the permittivity of H is equal to epsilon 1 and L is equal to epsilon 2. So thickness are equal for each layer. So let's say A is gallium arsenide and gallium aluminum arsenide. So epsilon 1 is equal to 13 and epsilon 2 is equal to 12. Similarly, if B is gallium arsenide and gallium arsenide, so epsilon 1 is equal to 13, epsilon 2 is equal to, sorry, this is glass, so this is 2.25. So size of band gap of photonic crystal A and V will be the band gap of A equal to band gap of V or whatever it is. So you can calculate this as a band gap increases, this delta epsilon is increase. Okay, so delta epsilon is greater than for A, so band gap of A will be greater than band gap of B. So this third answer will be the correct one. Okay, so similarly the question number 7, the periodicity 100 nanometer and epsilon 1 and epsilon 2 stack less photonic band gap, range of normalized 0.15 to 0.25. So range of wavelength of maximum reflection. So for that you can calculate this A by lambda, that is 2 pi omega. This is normalized frequency called normalized frequency, which is here given 0.15. So A by lambda is given 0.15. So from here you can calculate this lambda 1 is equal to this one and lambda 2 is 400. So from here this answer will be the correct one, 400 to 650 nanometer. Similarly the question number 8, this photonic band gap is called forbidden energy gap in photonic crystal. Defect states be created in the material to create or allow the energy state within the photonic band gap. So the increasing the thickness of one layer to the another stack layer, or changing the permittivity of one of the layer, decreasing the thickness of one of the layer, and change the periodicity of the stacked layer. So due to defect what will happen? So due to defect this line will comes inside this one. So decreasing the thickness of one of the layer, this question is the photonic band gap is called forbidden energy gap in photonic crystal. Defect state can be created in the material to create or allow the energy state within the photonic band gap. So increasing the thickness of one layer to the other stack layer, it can be also be a defect, and changing the permittivity of one of the layer, this is also called defect, and decreasing the thickness of one of the layer, this is also called defect. So all these three ways to create the defect, but change in periodicity is different thing. So defect is not can be created by the changing the periodicity. Okay, so due to this reason these three are question answer are correct. And this question number 9, a diffracting grating has 100 slits, periodicity of 2.5 micrometer, so 2 second order maxima. So this theta will be plus minus 30 degree. What will be the lambda? So we know this theta is equal to 3 degree, 30 degree. So order of maxima is n lambda is equal to d sine theta. Okay, so n is equal to 2 is given, second order. So d is 2.5. So 2 lambda will be 2.5 micrometer into sine 30. So this will be 2.5, and this lambda is 625 nanometer. Okay. Similarly, question number 10, it is given these 20 layers of stacks are given like that: n1, n2, n1, n2. There n1 is 1.5, n2 is 2, and this theta is equal to 45 degrees given. Okay, so what is the theta 20? So for Snell's law, you can write n naught theta 1 is equal to n1 theta 2 is equal to n2 sine theta 3, like that, equal to n2 sine theta 19 is equal to n0 sine theta 30, because this is again the air. So according to this formula, this equal to this, and you can calculate this n0 is cut by n0. So sine theta 1 is equal to sine theta 20. So theta 1 is equal to theta 20, that is 45 degree. Okay, so this is from simple Snell's law. And here are some questions. So okay, so this is the all questions which I discussed in my uh, class when it was online, and I will also add some video here for the fabrication process, so please refer it. Thank you. So if we see the fabrication methods for nanomaterials, so badly it is divided in two parts: top down methods and bottom. So top down methods is the photolithography methods and scanning lithography. It is also known e-beam lithography and soft lithography. So all the lithography parts comes in the category top down methods, in which nanomaterials are derived from bulk substrate and obtained by removing materials until the desired nanomaterials is obtained. So first we take the bulk materials, then we go to the nano size by removing the materials, while in the opposite other hand, bottom up methods, we go from the atomic and molecular level and then gradually assembling to the desired structures is formed. So chemical vapor deposition, sol gel synthesis, these are some methods comes under the bottom up methods. So here we will discuss the photolithography method. So in photolithography methods there are four key steps. Number one steps be first deposit the photoresist on the substrate, then with the help of one mask be exposed with the UV light around 365 nanometer, and then the exposed part, here the exposed part is this and unexposed part this dark one. So if it is a positive photoresist, then the exposed part removes, while in negative photoresist their unexposed parts remains, and the unexposed part uh, removed first. So after exposed after exposing, we develop with some chemical solution, or this is called bed etching, and sometimes we use the dry etching by oxygen plasma like things, and then after that we deposit some materials in this exposed part and then remove the remaining parts. So the structure is formed in the by photolithography in this process. So next one is scanning lithography. So in this we use the electron beam or high energy particles to scan, to pattern some part like electron beam, then we develops and then deposit the desired material and then lift off, so the pattern is formed. So this is called e-beam lithography. So but when we go with the halide perovskite, some of the problems which comes when we do the lithography with halide perovskites. So one of the problem is solidity in developer, because when we develop the resist, so some of halide perovskite dissolve in that one. So like PMMA, so for PMMA there are some which developer is used, so in step 2 and 3, so problem occurs in this step, while other problem is reaction with resist solvent. So photoresist is also thinning with some solvents, and these solvent dissolve this halide perovskite. So with some photoresist, step 1 is problematic like SU8, this is the negative photoresist, and other part is the degradation of perovskite in chemical used in lithography. So this is the main problem. So to avoid these problems, in this paper ACS Nano 2019, these people try to do the lithography with halide perovskite with some modified way. So they found that the PMMA can be used to prevent perovskite. So with the problem, so you can prevent in first step by PMMA. After that, SU8 can be used, for which step 2 and 3 is not problematic. For SU8, the first step in which the photoresist is deposited on the substrate is the problematic. So they use the two resist PMMA and SU8 simultaneously to do the photolithography while using dry etching. So the chemical is the chemical creates the problem by degrading this halide perovskite. So they use the dry etching to show oxygen plasma and organ milling the process to etch the material in this litho paper. So next, so they like pattern the single color disc. So here they use one perovskite which is methyl ammonium lead bromide. So this gives the green color. So when first they uh, spin coat this material on the glass substrate. After that they do spin coat 1 PMMA layer of 710 nanometer, and after that isolate photoresist of 400 nanometer. Then they exposed, so this is the negative photoresist, so this exposed part will not removed after exposing. So after exposing they develop in this EC chemical to SU8. So SU8 is removed, unexposed SU8 is removed from this. After that, to remove this PMMA, they use O2 plasma etching. So PMMA is used to remove this PMMA. After that, organ milling is used to remove this perovskite. So we can see this is the structure we want to deposit. So after that, this remaining PMMA and SU8 is again removed by oxygen plasma and with some toluene bars. So the surface profilometry is done. So we can see they found some flat surface on this perovskite with the height of so surface height here, and to ensure that the degradation is not done, the photoluminescence quantum yield were calculated. So for the freeze for halide perovskite it is around 55, and after developing it is found 45, so not much degrading in quantum yield. So next, so the control over this feature geometry is they pattern the different size of micro discs from 3 micrometer to 17 micrometer, and from the surface profilometry they found the 220 nanometer, which is the height of this perovskite film. So it means the PMMA and SU8 removed completely, and also the quantum yield much did not uh, did not degrade much. So and also they calculate the surface roughness, and they found 1.6 nanometer over a 15 micrometer scan and 4.5 nanometer of roughness over 500 micrometer scan. So from this these quantity are already published in the literature that in some standard method this much roughness is found for the halide perovskite. So we can say that this method is efficient uh, with some standard uh, methods. So to control this size of this disk, they also use e-beam lithography instead of UV lithography, and they found the size of 1.1 micrometer is can be achieved very good feature size. So but when we go to the application in display and camera sensor, so we have to pattern the different type of colors. So we use the different perovskite like green perovskite and the blue perovskite. So but the problem is the perovskite which dissolved the uh, blue one also dissolve this green one. So to pattern this, we have to first prevent the first deposited pattern. So for that we use the PMMA and SU8 over this patterned uh, patterned disk. Then after that, with some greater radius of this height we expose, and we found this is prevent also with the side walls. Then we deposit the blue perovskite or spin coat, and after the same process is followed to found the two different color of disc. So here is the picture in which the green and blue is simultaneously patterned on the same chip. So conclusion is that by combining badly available resist with the use of PMMA protection layer, we can achieve the excellent quality feature of the halide perovskite with the lithography process, and the causer of minor degradation of the perovskite, uh, but in this form not much degradation, but the minor degradation is found, and we can see the quantum yield degraded from 55% to 45%, and the patterning of perovskite film much more accessible to the wider scientific community with this lithography process. And also this can be used in uh, commercial purpose, and this enables the wealth of potential application for the perovskite. So this is all this presentation. Thank you. Second order Z2 correlation tau, if we have beam intensity with I at time t, this is the intensity at time t, then this G2 can be defined like G2 tau is equal to average of I at time t and intensity at time t plus tau upon intensity at time t square. Okay, so where the this bracket is denotes the time average. Okay, time average of the quantity which is written inside the cavity in this bracket. Okay, so from an experimental point of view, if we see this point of view, the number of counts, that is n at time t, registered on a photon counting detector is proportional to the intensity of the impinging beam. Okay, so we can write this classical definition of G2 tau as nt and n at t plus tau divided by time average of nt. Okay, so what is the physical meaning of this one? So we can think this g2 tau as a answering the following question, like I have detected a photon at a time t. What is the probability of detecting another photon at time t plus tau? Like if we are uh, detecting some photon at time t, then what is the probability that we also get the photon at t plus tau time? Okay, so so more precisely, if you see, this G2T gives us the degree of correlation between the number of photons detected at time t and at time t plus tau. So this tells us how much the information about the number of photons at time t translates into knowledge of what I will measure at time t plus tau. Okay, so the important note here is a very important value is g2 at tau is equal to 0. Okay, so however, in the way we defining g2, this is also kind of ill definition. If I have measured n photons at time t, what does it means to ask how many photons will be measured at time t plus 0 or at time t? So I will interrupt it in the following, as the number of photon counts at an infinitesimal small time after t. Okay, so what should be the value of g2? Generally we will see. So if the light is bunched, okay, then this g2 0, this will be greater than 1. So this denotes the classical phenomena of light or classical optics. Okay, phenomena. Second one is coherent light. Okay, so for coherent light, if you see, then this g2 0, this will give you this g2 value is 1. Okay, similarly for anti-bunching, or we will see single photon emitter, this is anti-bunch light, so this g2 0, this will be less than 1. Okay, so like for example, this is the time axis. Okay, then this is the tau c, that is coherent, temporal coherent light. Okay, then let's see three type of phenomena. So these two photons, and we will see these three photons is here, and if we see, one photon is at here, and one photon is here, and one photon is here. Similarly in this line, and similarly in this line. Okay, so this photon detector as a function of time anti-bunched, this will be anti-bunch, and this will be randomly, and this will be bunched light. Okay, so what is the difference? The difference is, for bunched light, this phenomena can be happens, this g2 will be greater than 1. Okay, so this for coherent light, like the produced by a laser, the number of photon counts is proportional to the intensity. Okay, so which is why definition in a simple scenario considered here, the constant over time. Okay, so this means that the number of counts at time t and t plus tau are uncorrelated. Hence this G2 tau will be 1 for any tau value. So note that the average number of counts are not uncorrelated in general, and indeed in the simple example of the beam with constant intensity that we are considering here, the averages are constant. Okay, so still the function of the intensity are uncorrelated. So this means that no matter how well I know the distribution of intensity at time t, one will never be able to reduce any uncertainty about the intensity fluctuation at time t plus d tau. Okay, so now this G20 tells us how often we detect two photon at time very close to each other. Okay, so we imagine here to always detect one or zero photon at a time. So while for coherent light the two detector events are uncorrelated, for light produced by other kinds of classical source like chaotic light, or we can have intensity fluctuation on the source, and therefore a tendency of detection events to be sometimes closer to each other. So in these cases one talks of bunched light. Okay, so this means that given a detection event at t, there is a higher probability of another detection event at time t close to t. So this kind of source therefore satisfies G20 is greater than 1. Indeed, it can be shown that classical light source must always satisfy this condition. Okay, so this is mostly classical light condition. So this means that in the classical view of light, this G20 is always less than 1, that is anti-bunched light is not possible. Okay, so why it is important we are talking so much about this G2? So from this last statement we can now see that importance of the this parameter. It allows us to experimentally rule out the classical view of light. Okay, so if we manage experimentally detect anti-bunched light, then we must surrender and admit the necessity of the quantum picture. Okay, so which of course is what actually happened about the experimental detection of anti-bunched light. We sir talked about this Hanbury, Brown and Twist experiment. Okay, so in this experiment one uh, uh, beam splitter is here, one detector is this way and one detector is in here. So this the probability of getting, if the single photon is coming at a time, then it can go either here or either here. So probability at 1 is 0 and probability is half that it come to the one detector. But if it detected by one detector, another detector should be 0. Okay, so this is the important of G2 is we can define and about the classical light and the quantum light nature of the source by using the value of G2. Okay, so that is the some key aspects of this G2 which sir discussed. So now comes to the question. uh, Question number 1 is uh, temporal coherence manifest itself as. So options are: A is a degree of monochromicity of the light, okay, and B is angular speed of light beam. Similarly, this C is the fluctuation in the photon number due to the discrete nature of photons. Similarly, the D option is the spectral width of light. Okay, the option E is the photon energy of the light beam. So temporal coherence, as I talked earlier, the degree of monochromicity of the light is somewhat related to the temporal coherence. Another is spectral width of light. As I say, this tau c and delta f is should be less than 1. Okay, with this relation, sorry, this greater than 1. Okay, so from which you can write these two are the correct answer. Okay, similarly we have question number 2. So question number 2 is the visibility of fringes in Young's double slit experiment is manifested of light. So your options are statistical nature, option B are quantum nature, option C are spatial coherence, and option D is temporal coherence. So as I see earlier, this Young's double slit experiment, whatever this part difference is given by this distance d between two slit, so it means this manifest as a spatial coherence. Okay, so spatial coherence is the correct answer. So statistical nature, I don't think this visibility of fringes can be explained on the wave nature, right? So it does not manifest as a quantum nature of light, as well as temporal coherence also is not valid, and this statistical nature is also not valid for this. No need of this statistical nature to define the Young's double slit experiment. Okay, so we can eliminate these three option, and the correct answer we can choose statistical coherence. Okay. So next in question 3. Question 3 is the delay over which the correlation in phase or amplitude of a wave decreased by a significant amount is defined as. So your options are A, coherence time, tau c, B is coherence length, which is LC, C is pulse width, and D is wavelength of the light, and E is coherence area. Okay, so what will be your answer? The question is the delay over which the correlation in phase or amplitude of a wave decreased by a significant amount. Okay, so this delay is related to time. Okay, so this is coherence time, so this will be the right answer, coherence time. Okay, so next question, question 4. Question 4 is given that consider the following source which is Si with corresponding coherence time tau ci. Okay, so choose the correct answer. The source 1 is given LED, which is delta lambda is somewhat 50 nanometer. Okay, source 2 is given tungsten filament, and spectral width is around 600 nanometer. As 3 is given sun, which this delta lambda is around 1 mm, and as 4, source 4 is given laser, that is delta lambda is 5 nanometer. Okay, so what will be the answer? we have to arrange. Okay, first I give to the so option 1 is tau c1 is less than tau c2 is less than tau c3 is less than tau c4. The v is tau c4 is less than tau c1 is less than tau c2 is less than tau c3. Okay, third is tau c3 is less than tau c2 is less than tau c1 is less than tau c4. And option D is tau c1 is equal to tau c2 is equal to tau c3 equal to tau c4. And E is tau c4 is less than tau c3 is less than tau c2 is less than tau c1. So as I earlier told you, this tau c delta f should be greater than 1. So this tau c is somewhat is greater than 1 by delta f. Okay, so this delta f is given by this. So whatever delta f is less, tau c will be higher. So for the laser will be the highest tau c. So this tau c4 is highest in these two. So all these answers are incorrect. Other than and 5, then is less than this is 50 nanometer. So this S1 will be second highest. So this is only in this one. So this will be the correct answer. Okay. So this question number 4. Sorry, question number 5. Question number 5 is given. The correct mathematical expression for second order correlation function G2 tau is options are A, G2 tau is equal to ET plus tau divided by IT plus tau. The V option is G2 tau is equal to ET plus tau divided by ET plus tau. The C option is G2 tau equal to IT plus tau divided by it plus tau. Option D is G2 tau is equal to ET IT plus tau divided by IT plus tau. And the fifth G2 tau is equal to IT and IT plus tau divided by IT plus tau. So which one will be the correct answer is the question. Okay, so this is E amplitude, but G2 tau is the intensity fluctuation, measure of intensity fluctuation. So this will wrong. G2 tau always E, so this will also wrong. And here if you see, this is given equal to 1, right? So this is also not expression for G2T. So and here is also E is coming amplitude, so this is also right. So this will be your correct answer. Okay, so always this G2 is the IT plus tau and divided by IT and IT plus tau. Okay, so next question number 6. Light is said to be bunched if this G2 tau is less than G2 0, G2 tau is greater than G2 0, G2 tau equal to G2 0, and D is G2 tau equal to 1, and E is G2 tau equal to 0. So the correct answer will be this one, as I discussed earlier also. So question number 7 is this light is said to be anti-bunched if option A is G2 tau is less than G2 0, V is G2 tau is greater than G2 0, C G2 tau is equal to G2 0, and D is G2 tau equal to 1, and E is G2 tau equal to 0. So the correct answer is this one. Okay, for anti-burst we study that G20 is less than 1. Okay, question number 8 next. The classical Hanbury Brown twist HVT interferometer the options are exhibits interference pattern, the V's measures cross correlation, and C's measures autocorrelation. Between electric field and cross correlation between photocurrent and these measure autocorrelation between photocurrent is measure correlation cross correlation between electric field. So as sir already discussed in the class, this HVT is somewhat one detector in this way and one detector in this way. So whatever photon comes on this one, we use simply like photodetectors. So photodetectors generates the photocurrent. So whatever we measure, that is photocurrent, not the electric field. So these two answer is eliminated by this thing. And interference pattern also did not detect here, because we detect only number of photons whichever comes on this detector and the number of photons whichever in this on this one. Okay, so we know this. So from this what we know, measure the cross correlation or the auto correlation, that is the question. Okay, so we measure the cross correlation. Okay, so this is the right answer here, because cross correlation means like we measure either coming on this one or coming in this one. So what for any detector, if the photon is detected in t plus tau, so that is somewhat this cross correlation, not the auto correlation. Okay, so next question is question 9. So question 9 is, for a given monochromatic light wave with a constant intensity E0, the value of G20 is. So question is, for given monochromatic light wave with a constant intensity A0, comma, the value of G20 is. Options are A0 by 2, V A0 square, C is 1, D is 2A0, and E is 0. So the correct answer is 1. How? So how? The question is how. So just consider this amplitude is like something like that. So this is A0, okay? So this is constant. So G2, so I at time t will be A0 square, okay? So this is constant. So I at t plus tau is also will be A0 square, right? So sorry, this is intensity, okay? So this is not the A0 square, this is simply A0, okay? So this G2 at 0, if we'll see, so this will be at tau, this will be at time t, I at t plus tau equal to this I at time t square, right? So if we put tau equal to 0, then it will be I t ka whole square time average and I t time average of whole square. So this will be A0 square by A0 square, and it comes 1, okay? Remember? So next question number 10. So calculate the value of G20 for a monochromatic light wave with a square wave intensity modulation of plus minus 20%, okay? So your option is A 1.04, B 0.8, C is 1, D is 0.2 and E is 0. So what will be the question? Just solve in 5 minutes. Hello.